Okay, so let's start today. So I'll briefly describe a tautology checker, which is available for you to do this, for you to play around with. Maybe it's written in ML, but besides, I mean, so this is the only piece of actual program code that I will be discussing. The rest you will be writing. So it's a good idea to see how our whatever we have done so far is used in this tautology checking. Right. So firstly, of course, let's look at tautology checking. Let's go straight to this. Um, so so essentially, what we are interested finally in the question of whether a certain argument is valid. That is the most important thing. You're given a set of assumptions, and then there is some conclusion you come to, and you want to know whether that conclusion logically follows from this set of assumptions. Yeah. So of course, so so a typical informally stated argument is something like this. I mean, it's really awful when you state it in natural language. I mean, there are all kinds of things. I'll just read it because if in case it's too small for you to read. If prices rise, then the poor and the salaried class will be unhappy. If taxes are increased, then the businessmen will be unhappy. If the poor and the salaried class or the businessmen are unhappy, the government will not be re-elected. Inflation will rise if government expenditure exceeds its revenue. Government expenditure will exceed its revenue unless taxes are increased, or the government resorts to deficit financing or takes a loan from the IMF to cover the deficit. If the government resorts to deficit financing, then inflation will rise. If inflation rises, the prices will also rise. The government will get re-elected. Therefore, the government will take a loan from the IMF. Right? I mean, now if this were an argument that actually came in some newspaper article, the question of whether the conclusion is valid is from the whatever assumptions that the author has made is extremely difficult to find. I mean, right? So to prove the validity or the invalidity of this argument and the conclusion is actually very hard. Of course, what there are some things. This is written in natural language, which means that firstly one has to sort of clean up ambiguities and so on and so forth, and maybe one will have to reword it, retranslate it to some more sensible logical form, so that the ambiguities of language are eliminated. That is one thing. So this is a common problem with all natural language kind of arguments. Yeah. Right. So the other thing is, in order to know whether it's valid, basically what we are asking is whether this last statement, therefore the government will take a loan from the IMF, follows from all these other statements. Yeah, all of them are declarative in nature, of course, so essentially what we are asking is whether the last statement is a logical consequence of the previous statements. And for logical consequence, we have a number of different possibilities. One, of course, is that by definition you're basically looking at a world in which all the hypotheses are true, and then you're asking whether in that world it is always guaranteed that the conclusion would also be true, and that is what the definition says. The other possibility is, of course, to use one of these other theorems that we have got. One is to take all the hypotheses and take their conjunction and see whether conditional to the conclusion, whether what you get is a tautology. So that's why for checking validity of arguments, you can use the notion of a tautology, at least propositional arguments. It's not necessarily true for other kinds of arguments. So for propositional arguments, you're just asking whether the conjunction of the hypothesis logically implies the conclusion. So this being a tautology is equivalent to saying that this logically implies the conclusion. Yeah. Uh, there is of course there are of course other means. For example, these theorems tell us other ways. One thing is to actually look at this whole thing conditionally, right? It's just conditionally and check whether uh, this is a valid formula. This is also a question of checking whether this is a tautology. Uh, and the other possibility is to actually take the negation of the conclusion along with the conjunction of the hypothesis and check whether you have a contradiction. I mean, so these are essentially three different ways in which most checkers and provers work, right? So what we'll do is we'll take the previous one, namely this, and we will use this as in order to as the principal way of designing a tool. Yeah. Okay. So um, right. So this is using essentially theorem. So you have, so one possibility is of course is to use the truth table, right? One, I mean, just construct a massive truth table and check for validity. I mean, check all the rows. I mean, yeah, but what happens is, and but the other problem is, it's not just enough to say that this argument is, if it is valid, of course, it's enough to say that it's valid. But if it is not valid, it is not enough to say that it is not valid. So if it is not valid, that means you have to provide a scenario in which all the hypotheses are true and the conclusion is false. So which means what we need to do is, in order a complete checker would actually give a falsifying assignment in case the argument is invalid. So that is an important aspect, and in fact this is an aspect that is normally not addressed by theorem provers, because theorem provers just prove theorems. But there is another field of computer science which is getting to be very popular now, and that is the notion of model checking. So in the area of model checking, when you have some logical statement, if it is not true, then you have to provide a counter example. In the case of propositional logic, what we are asking is a falsifying assignment. So it is the equivalent. So what we are doing in our tautology checking is to provide the equivalent of a model checking mechanism. So if it is true, it will definitely verify it, but if it is false, then it has to provide a falsifying, it has to provide a counterexample or a falsifying assignment or some other proof that it is indeed false, and that proof is something that should be able to check. So in this particular case, we are looking for essentially a falsifying assignment which will make the argument which will show that clearly that the argument is invalid. Yeah, right. Okay, so one thing of course is that you have to, as I said, clean up the argument and translate it into an argument involving only the propositional connectives. So which also means you have to identify what are known as the atoms in the argument. What are the atomic propositions which can be taken for granted, which do not have to be split anymore. So you have to split sentences in terms of the propositional connectives like and or if then or not, and you have to actually identify atomic statements whose truth values could be anything. So, and since you are looking at validity, so one thing of course, so that part of that cleaning up is to essentially identify the atoms in the argument. So here is a simple identification. So we have got so many atoms which are so I will use essentially strings taken from the argument as atomic statements which cannot be split further into sub-statement. Right. So these are the atoms in the argument identified in some way, and we already see that there are nine atoms. So your truth table is going to be quite enormous. It's going to have 512 rows, and of course I don't know, since there are compound compound propositions, there are going to be that many columns. So it's going to be a huge truth table consisting of about a few thousand cells, right. Now the point is, it's not actually necessary to construct the entire truth table. That's one thing. So therefore, of course, none of the algorithms that we are going to design is anyway going to be less than exponential. Okay, so that is going to be a bottom line, but that's not what we are saying. But in practice, what we are saying is, so firstly, it's not necessary to consider construct the entire truth table. So it's only necessary to consider possible falsifiers, and if there are no falsifiers, essentially the argument is valid, right. So it's possible to do tautology checking in some more disciplined fashion, and that's what we have to look at, yeah, right. And as far as the basic representation is concerned, we represent propositions as abstract syntax trees using standard data type, a recursive data type definition, which is essentially a reflection of the grammar which was used for the design of abstract syntax trees. So there is an atom of string, and after that the rest are all connectives, which with obvious meanings that we can attribute to them. Not is negation, and is and or is or, imp is conditional, and equal. You're really sauntering, as if into a bar or something. Right. So this is our we can use this as a standard representation. This way, what I'm going to I don't need to worry about the initial aspects of scanning and parsing, whatever the argument. We just have a representation in terms of this data type, and that directly gives you your abstract syntax trees, right. So essentially the propositions will be formed from these atoms, right. Okay, and so if a propositional rendering, which without going into the other kind aspects of the translation, essentially gives you a sequence of hypotheses like this. So there are 8 hypotheses, and these are the compound propositions. So if you look at all the sub propositions, sub formulae that these 8 hypotheses have, the conclusion seems to be is just an atomic one, right. But if you look at all the sub formulae that you have, any truth table construction will require columns for each of the sub formulae also, right. I mean, so that's how you will build up the truth values of the full formula, right. So if you look at all those sub formulae, then essentially what you have is something like we had 9 atoms and maybe something like 12 or 13 different kinds of sub formulae, because this hypothesis 5, for example, has 4 sub formulae at least, because there are 4 operators there. This thing has hypothesis 3 has 3 sub formulae at least, and so any truth table construction would actually have your 512 rows for this, and multiplied by 13 or 14 columns and then after that you will require some more columns, because what you are going to do is you will have to take the conjunction of all these hypotheses and the conclusion. So that might be 15 or 16 columns, and then essentially find the truth value of the argument, right, and that can be quite huge. So it will be a few thousand cells. We do not want to do that. We want to do a more so to speak, logical or deductive way of doing tautology checking, all right. Okay. So essentially we need to show that, I'm sorry, this one has not come out right. So an argument, as far as I am concerned, is a list of hypotheses and a conclusion. Yeah. So, it is an ordered pair of a list of hypotheses and a conclusion, where both the list is a list of propositions and the conclusion is also a proposition. Yeah. So, essentially what we are going to do is we are going to do an argument is a big AND of all the hypotheses, where H is the set of the list of hypotheses, and essentially we are saying that you take the conjunction of the hypothesis and show that the implication, show that this conjunction implies the conclusion, right. So, I can so there is a so I can define a function called which does a big AND. And what we are going to do is, so you take this, so essentially there are of course trivial cases where you might just have a conclusion. I mean, that's a trivial case of just claiming that some proposition is a tautology, right. So this is what, so an argument is valid provided you take this implication and prove that it is a tautology. Of course, the result of checking whether it is a tautology is just going to be a true or false result, and that is not sufficient. Yeah, if it is false, then we also require to use falsification. So here is a function to falsify an argument, which essentially checks whether the conjunctive normal form of this entire proposition big AND of H implies P, whether that conjunctive normal form can be falsified. So this is one possible strategy. I mean, not necessarily the best strategy, but this is one possible strategy. Yeah, and this is the strategy that I have adopted, right. Okay, but there is a problem here. The big AND gives me conjunctive normal forms very easily, but the fact that the big AND has to imply something essentially means when I replace the arrow, then I will get a negation of the big AND, which will be a big OR, right. And then if I have to take the conjunctive normal form of that, essentially that formula will explode, right. It will, because I will have to distribute the OR, I will have to push it down in order to get the conjunctive normal form, right. Okay, but anyway we are going to do that, right. So the actual checking of tautology therefore reduces to, I can get rid of that tautology function and just look at falsification, because anyway I have to do falsification if there is going to be any proof. So what do I do? I take the entire argument represented as a proposition and I take its conjunctive normal form and check whether I can falsify it, okay. And if I can falsify it, then it is then that itself gives me a falsifying assignment, right? An assignment which will give me a truth assignment for the individual atoms, which ensures from which I know that the argument is invalid, and that can be checked, for example manually if you like, if you have enough time, right. So if the result of falsification is an empty list, that means there is no possible falsification and therefore it is a tautology, right. So this is the way this tautology checker works, yeah, right. So falsification is an important aspect. It is not just checking validity of argument, yeah, and I use the falsification in order to determine whether something is a tautology, yeah, right. So one thing, of course, computing the CNF, taking any propositional logic, taking any element of that data type of propositions, basically we have to define rewrite rules. One is of course pushing down negation, and when you push down negation then your ORs and ANDs get inverted. But before that what you need to do is you have to rewrite all the implications and equivalences. Rewrite implications and equivalences in terms of ANDs, ORs and NOTs, and after that you just push down all the negations so that you get at the bottom of the tree only literals, right, and there is no negation upwards above. So, there is a frontier of negations which gets created, and above it, since there are no other operators, they can only be ands and ors. And of course, what you can do is once you distribute all the ors over the ands, you get a stratified formula, something like what I said. You would get essentially a stratified formula like this. And what the big AND does, is it actually flattens this tree to a lists of literals, right. So the big AND essentially just flattens this tree into a list of literals. So now I am essentially dealing with lists of literals, right. Okay. So the list of literals means basically that you have a list of conjuncts, and each conjunct is a disjunction of literals, right, and so you have a list of literals, and you have to look at those literals in that way. So when you do all this, so you will get essentially this list. So how do you do falsification? So essentially what we had, so the whole idea now of the tautology checker has moved from actually determining whether it's a formula is a tautology to just checking whether it can be falsified, right. So falsification is the important thing, and basically if it cannot be falsified, then it's a tautology, right. So one thing is true, so you have a CNF, and in order to falsify this CNF, it suffices to find just one conjunct in this CNF which is false, right. So since it's a conjunction of essentially disjunctions, it's necessary to find just one of those to be false, okay. Now when is a disjunct false? That's where the complication comes. A disjunct is false if and only if it doesn't have what is known as a complementary pair. So okay, so if it contains a complementary pair, that means if it contains both a positive for some atom P, it contains both P and not P, then the disjunction of P and not P is anyway true. So that disjunct can never be false. However, if that disjunct consists of just completely disjoint literals with no common atoms, so all the atoms in all the literals are unique, then it is possible to falsify it by setting all those literals false, which means the positive atoms you set them to false and the negative atoms you set them to true, right. So then you can, because the only way a disjunction can be falsified is if all the literals in the disjunction are false, and the way to do that is to ensure that. So now the problem therefore just reduces, so then it can be falsified, but we do not need to actually do that, it is just enough to check whether there is a complementary pair or not. So if there is no complementary pair, then it can be falsified, and therefore there is no problem, right. So this is what, so you take these literals in any disjunct. So let us say you take a disjunct Di and just partition it into the positive and the negative literals. So in fact once you have partitioned it, you can even remove the negation sign from the literals. So you partition it into two sets of atoms, one set of atoms is Pi and the other set of atoms is Ni, and all you check is whether they have any common element, right. So what I am saying is that, so this is what actually the tautology checker does. So now the falsification of the CNF reduces essentially to just checking whether there are common elements in two lists. Yeah.
Sir, essentially this you are checking for common elements. So sir, how are you falsifying all the atoms as a whole?
No, then basically the way to falsify all the atoms is to, as I said, assign to all the positive atoms the value false, and all the negative the atoms which occur in negative form, assign them true. So you get a falsifying assignment which will make at least one conjunct false, and that's it, that's enough. It makes a disjunct false, but then you have a conjunction of disjunctions, so one of the disjuncts has to be made false, that's right. So essentially what we are saying is, so if I have a list of lists, if I have some list of lists of this form, so this is essentially lists of this kind which contain literals, and this brown one is essentially an AND of all these lists. Each of these green ones is an OR of all the literals inside. You might have various literals L11, L12 and so on and so forth, L21 and so on and so forth, and these literals I am partitioning each of these to check. In order to check whether this whole thing can be falsified, I need to just go through this list and check whether any one of them can be falsified. So if I find, let us say this one, if I find that this cannot be falsified, the only way it cannot be falsified is because there are two literals L1I and L1J which are actually complementary pairs. That is the only way this cannot be falsified. Cannot be falsified means it is always true, right? So that is what happens. So I go through these, and if I find this, the atoms of this are all distinct, then I know that it can be falsified. And how can I falsify it? I can falsify it provided all the each literal is assigned the value 0, is assigned a truth value 0. And in order to assign each literal the truth value 0, I take the positive literals, they are just atoms, and I assign them the truth value 0. I take the negative literals and take the atoms and assign them 1, and therefore I have got a part assignment of a subset of the atoms in the entire proposition which will guarantee the falsification of one of the disjunct. And basically for all other atoms, I do not care what assignment is done. Whatever other assignment may be done of truth values, this disjunct is still guaranteed to be false, and therefore that is a falsifying assignment. So it's that's exactly what happens in this case. Yeah.
This concept is clear.
Yeah.
The only problem that I cannot understand is that when you are specifying a literal, don't we inherently assume that it is true?
No. Why should we?
Like,
Why should we?
written a literal that the government will be re-elected.
Yeah. So
Don't you specifically think that the atom is true?
no, what we are no, all that we are saying is, so see that happens to be an atom, right? But what I am saying is, look at this complicated thing, man. There is which has a lot of ORs in it, right? Now even if this complicated, there is a way of, you take this statement, I can zoom this way. Okay, it comes down to this. It has so many ORs in it that even if I assume that this entire proposition is true, it is not, it's quite possible that some of this proposition can be made true only by by assigning certain atoms false value, right. Supposing there is a negation there, right. I mean, so it's there is no guarantee that you have to assign all the atoms the value true, no, right. Some of the, in fact, there are various assignments in which this can be true, in which some of the atoms could be true. In fact, since this contains two ORs, basically any truth assignment in which at least one of the atoms is assigned true would make this true, right. I mean, so that is not really the important thing. What we are saying about validity is just that in the set of all truth assignments in which all these hypotheses are true, is the conclusion also true? That's all we are asking. How all these hypotheses are true can be because of certain atoms being assigned a false value, a false truth value. Okay. So let me just. Yeah. So we are going to use this tautology too, which essentially relies on falsification, and this is the strategy that the tautology checker actually employs. So if you read the source code of the checker, actually you will find this. So there is a partitioning of the list of literals into two sets of atoms. So the pi and the ni are actually atoms, and basically there is a one higher order function which checks for disjointness, right. Right. So this is how this tautology checker works. Yeah.
The algorithm we just discussed for falsification, doesn't it seem to be a polynomial time algorithm?
Actually, polynomial in what? You have to look at the measures. So once I have converted things into CNF, in terms of this CNF, it is polynomial time. Okay. But the main problem is converting things into CNF that can double sizes. So if I had especially look at this, the implication of a big AND. So a huge number of, you can have a huge number of hypotheses, and you take this implication, which means first you rewrite this implication by negating the big AND negation of the big AND makes it a big OR. Then you want a CNF, which means you have to distribute that OR, and then there you are exploding the number of terms, the length of the formula. That is where the problem is. So the conversion into CNF can actually explode the formula size, right. But otherwise what you are saying is right. Just given, so if you look at the complexity of this method just in terms of given a CNF and the length of the CNF, then it is polynomial on the length of the CNF. But if you look at the size of the original argument, then it could be exponential in the size of the original argument. Yeah. So it is important to actually get to know what is your measure. Are you looking at the size of the CNF as n and determining the complexity in terms of that n, or are you looking at the size of the original argument as n and then determining this? And also there is this question of sometimes things are different. I mean, between the number of atoms, there might be you might have different complexities based on the number of atoms and the number of connectives, right. I mean, you might have to separate the two also, because your explosion, the number of atoms is fixed initially, right. The explosion happens because of the connectives, right. So it's exponential anyway if I look at it as in terms of the size of the original argument. Okay. The only thing I can do is try to restrict it. For example, but the actual tautology checker code, if you look at it, it doesn't stop with finding one falsifying assignment. It actually finds all falsifying assignments. Okay, and the way the falsifying assignments are actually found is by just listing each is just by listing all the positive atoms and assuming that all other atoms are negative. After all, I mean, look at this strategy. So what you are saying here is I split this list into a collection of positive atoms and a collection of negative atoms and check whether they are disjoint, right? And supposing they are not disjoint, supposing they are disjoint, then I actually do an assignment. I can actually do an assignment, but then there might be atoms in these things which are not mentioned in this list. Okay, so what do I specify in the list? Just the atoms which have to be set true, assuming that all other atoms that occur in the proposition are set to false. Okay, so actually I don't even find all, I do find many other, so I go through all the lists in order to find various falsifying assignments, but not necessarily all of them. Okay, so that's why it's important to check the emptiness of this list. Where is that? It's important to check the emptiness of, this is a list of lists. Okay, so what it actually gives me is, it gives me a Boolean value false and a list of lists, where each list within this list is essentially specifies which of the atoms have been assigned true. That's it, right? So it does not check all the falsifying assignments necessarily, but it does check all the conjuncts. Okay, and gives you and essentially this LL tells you, each list inside this LL tells you which of the atoms have to be assigned true, and leaves all the other, assumes that all the other atoms are assigned false or leaves them unspecified. Okay, but it is necessary to actually set them all false, because otherwise you may not make this disjunct false, right? Okay, so there are those subtle things happening inside the tautology checker, but I don't necessarily find all possible falsifications. I just find some falsifications, but I go through all the conjuncts. So that basically I am finding some falsification for each conjunct if possible, wherever possible, and that's the lists of truth assignments that I give as the list LL. Yeah, otherwise, and if that list is empty, basically it means that I found a complementary pair, right? If that list is empty, basically it means I found a complementary pair. So that list of so in each conjunct there was at least one complementary pair, which means each of these regarded as disjunctions is true, and therefore this conjunction is true, and so therefore it's a tautology, right? Yeah.
Can there be multiple CNF forms for the same?
So if you think of CNF, because, okay, your AND and OR are both associative and commutative. So it's unique in the same way that numbers have a unique prime factorization up to order. Since we are considering lists as our data structure, actually there is an order, but further I impose an order on the atoms. I impose an artificial lexicographic order on the atoms, because atoms are all strings, right? So I impose an artificial lexicographic ordering. Therefore, actually I get lists which are unique, because they are ordered according to this lexicographic ordering. So there is a sorting also which happens in order to get a unique form. But those are internal details. We primarily need to view it as sets of literals, a set of sets of literals, and they have a unique form simply because of an artificial lexicographic ordering on the strings that I impose. There are other possible ways. One possible way is to just store all the atoms in an array in the order in which they appear and use the array index as your sorting order, for example, and use that throughout. I mean that might actually simplify the simplify carrying around strings. I mean carrying around strings is not particularly expensive, but it's easier to carry indexes, integer indexes than indices than carrying strings, for example. That's one thing. But I did not do that. I just used the strings themselves and I used a lexicographic ordering and I sorted. The best way to check disjointness, I required sorting, because the best way to check disjointness was to actually look at these two sorted lists, Pi and Ni, and just scan them once linearly to check disjointness, right? That's it. So I do impose a sorting without and I do a sorting without duplicates, because anyway your conjunction and disjunction are idempotent. So having duplicates around is useless. It just occupies space. So there are these cleaning up and bookkeeping operations that you need to do. So basically do a sorting without duplicates while you are creating the CNF itself, and so that your lists of literals are already in in a certain order. Also, I think my sorting, I had to write a sorting algorithm because I also considered all the positive literals as being less than all the negative literals, right. I mean, you have to have a total ordering on literals. So which means you have to do something about either I did that, or I interface the interleave the positive literals and the negative literals. I mean that's another total order. You can claim that P is less than not P, for example, and P is less than Q and not P is also less than Q, right. So you can impose various kinds of total orderings, whatever is convenient for the algorithm to check disjointness. But the crucial thing is checking disjointness. What is the easiest, simplest way in which one can do checking disjointness without doing very complicated algorithms like the ones you learn in a course on algorithms, because sorting is always a convenient thing for other purposes. I mean, just like when you do a course on algorithms, you have to find the k median or some such thing, and you're not allowed to sort it. But supposing I sort it, then I know the kth largest element immediately, right? But that has a complexity which is at least the complexity of the sorting algorithm, whereas finding the kth percentile or whatever can be done in less than the complexity of sorting. But sorting has other uses which do not allow me to which I can use, right. So for example, just the fact that I want a unique normal form, sorting helps me to do that, and then checking disjointness is linear time within that. So when you start going down deeper and deeper into the data structures, it's not enough to just look for the most efficient algorithm which will do a certain job, but whether the most convenient form can be used for other things. So one thing is, because of this lexicographic ordering, there is a unique representation. Because I do sorting, I can use that unique representation and I do sorting without duplicates. I sort of reduce the size of, I remove unnecessary redundant stuff, and it also helps me to do disjointness checking in linear time, and so on. Yeah, that's so those are decisions you take. I mean, in a typical course on analysis of algorithms, you don't look at the problem in context. Here you have to look at the problem in context. Is it really worth doing less than n log n? I mean, is it really worth not sorting the data structure? Is a question that you have to ask. Whereas if that sorting the data structure gives you some other benefits, it's better to do the sorting and then use that sorting itself then, right. Okay, so then let's go back briefly. So the other kinds of techniques that are normally used are these two. So one of the so many of you must have actually used this one. Yeah, this this B part of this theorem, you use it essentially in resolution theorem proving, right. So systems like Prolog use resolution theorem proving, right, and this is actually much more common because what it does, if you have already seen, if you already know how the Prolog system works, is that it allows you to do a directed computation with leading to a contradiction, whereas proving things otherwise can take you off the main direction. So the whole idea of doing a directed sub-goal computation in Prolog is to eventually reach that contradiction in some directed fashion, and so this is very useful for that. We will also see another method called called tableau methods, which were originally invented by the famous by a magician cum mathematician called Raymond Smullyan. Yeah, but now tableau methods have become extremely popular in the theorem proving era because they also use this theorem 4.3b and rise to give you a contradiction, but in a certain sense they are very fast, much faster than resolution. So it is not clear to me why, for example, but resolution also comes with other things like unification and so on, and therefore value bindings for a Prolog program, but more and more people are using tableau methods to prove things. So if you are just looking at provability, then tableau methods are very good. So what I will do next is actually a tableau method. I will start with a tableau method, and those tableau methods are also very useful for all other kinds of logics, because firstly they have the same advantage as resolution in providing you a directed means, and secondly they somehow seem in practice seem to work faster than resolution. Yeah. Okay, so I will essentially stop here. Are there any other questions? Yeah.
We had a doubt in the definition of functional completeness.
Yeah, there are. So I separated the two terms of adequacy and functional completeness. Many books treat them as the same. Okay, so what I did was I used what I thought was the set of operators, standard set of operators, and I defined adequacy in terms of that, and then functional completeness I defined as a level above. Okay, whereas most books treat them both as the same concept, and they just ask the question whether you got a functionally complete set of operators. So one thing is clear, that any adequate set of operators is also functionally complete. Okay,
that is because the omega is functional.
Yeah, that's because omega is functionally complete. Yeah, but I separated the two. That's all, because I thought we start with some standard and work downwards and upwards from the standard. That's all. Yeah. Any other questions? Okay, I think in one of my course home pages you will find this tautology checker code. You can see it. It's written in ML, and it essentially all this. You can see there are also comments in that code. You can see how actually the development takes place. Okay, we'll stop here.